Hey, welcome back. Today we're going to be talking about 3 ways to calculate the moment of inertia, including how to go about calculating the moment of inertia using something called the parallel axis theorem. And this is something you're going to need to know, especially if you're an AP Physics C mechanics student. So the first method we're going to go through has to do with just summing up the moment of inertia, or the rotational inertia, you could say, for all of the simple shapes and combine them into like a combination shape. And that's what we mean with this equation here. You've got the moment of inertia is equal to the sum of the mass times the radius squared. Now, what does this r value mean? Well, that would be the difference between the position of the center of mass and the axis of rotation. So I'm going to show you examples. In fact, I'm going to show you 6 examples with this lesson here about how to think through these various things, as well as videos if you want more information. I've got that as well for you. So let's go ahead and get to it. First of all, here we've got a combination shape. It could be called a complex shape, but it's really not that complex. You've got 2 masses right here, a mass here and a mass here, connected by a massless rod. And the question is, how would you go about figuring out what the moment of inertia is for this object here? Really crucial that we notice the axis of rotation where it's at. So if the axis of rotation is right here, you would get one answer. If it was, say, over here, you would get another answer. If it was somewhere in the middle or something like that, then you would get a different answer altogether. And that's because the mass is distributed differently from the axis of rotation in every case. Now, if something is directly at the axis of rotation, like this 3 kilogram mass in this example here, then that becomes irrelevant. Let me show you what I'm talking about. So you can read the problem here if you choose, but that's more or less how I was explaining it. We want to use this summation strategy here. So the sum of the moment of inertia for the first object, notice that is going to be a 0 for the r value. So that whole term goes away. This is going to be 5 kilograms at 3 meters squared. So if you do the math here, you end up with 45 kilograms times meters squared. Those are going to be the units for the moment of inertia, by the way. And that's how you would go about doing this first example 1a. Well, let's try another example by contrast so you can see the contrast to what we're talking about here. What if we had the axis of rotation over here? Notice we're actually going to get a different answer. So let's talk about that. If the axis of rotation is right here, we're still going to use this summation strategy. And if we do that, notice this time this r value is gone, but with the different masses, you're going to end up with a different number as our answer. So that's what we have for the second example. What if the axis of rotation was not like at one extreme to the left or to the right? What if it was somewhere near the middle? Well, let's try a problem like that as well. Let's say the axis of rotation is right here, about 1 meter from the left side of the compound object, or a complex object if you want to call it that, even though it's really simple. This bar, by the way, we're not accounting for this bar in this problem. We're making it as simple as possible. So we're just saying that the mass of the bar is insignificant compared to the masses of the objects on either side. So in this case, you're going to do a very similar type of calculation. You can see what's going on here. It's just that this value is going to be 1 meter from the center of mass for this object and the axis of rotation. This is going to be 2 meters, and so you can do them. And so if you're careful, you can plug in your numbers and come up with that summation answer over here. So, okay, so that's our first method. That's the easiest method. Let's get into something more difficult and show you a brief overview of how to think about this in terms of the calculus involved. So here we're going to integrate the little infinitesimally small pieces of mass and place them in little sort of positions, these little dr values. So let's talk through how to do this. The problem says calculate the moment of inertia, rotational inertia, for a long thin rod that rotates about the axis of rotation in the middle. And so there is a concept called linear density. So it's going to be mass divided by length. It's related to just density that you may have had as like a middle school student. Usually what we mean by that is mass divided by volume. So this is like the linear version of that in terms of one dimension. You could say it's one-dimensional density, this linear density. That's what we mean by it. So there's this concept, and we represent it by lambda over here, linear density, mass divided by length. And if we think about this m, we could call it a dm and this a dr. just to put them in slightly different variables here. The m, you can see the little m comes from the big M, that makes sense. And the r is going to be synonymous for the L over here. In other words, we're taking a general principle and applying it to the more specific example that we're going to be dealing with. And what I've done here is I've taken the infinitesimal of the numerator and the denominator. You can do that. In fact, in some problems, you're going to need to be able to do that. It's, in a way, combining concepts from algebra and calculus into sort of one step here. And what we're going to want to do is isolate for dm. We want to isolate for dm because the equation we have on our equation sheet is this. So this is our equation that we're given, and we need to isolate for dm. Notice that r and m are just, they're different variables. They're put in different ways, so we have to relate this to something else. That's effectively what we're doing here. So we take this that we have solved for in terms of dm, and we're going to sub it in for dm over here, and notice we get this. So you take the integral of r squared m over L in terms of dr. So let's continue with that. I've run out of room, so I'm going to put what we ended up with on the next page. The only thing that we have done here differently is notice I pulled out the m and the L out in front because those are constant. So when we're integrating, we can do that. We should do that. And we need to figure out what our upper and lower bounds are going to be. Now, our upper and lower bounds, in terms of this is supposed to be right in the middle. And so if that is the case, and this whole thing is L, this whole thing is like the length of the rod, then therefore the upper bound would be like a positive 1/2 L, and the lower bound would be like a negative 1/2 L. So that's why I have the bounds that we do. So we can start to integrate this and evaluate it at those bounds. So we plug in our numbers, and I'm running out of room here, so I'm going to briefly show you. You can pause the screen if you choose, and then we're going to continue and finish off the problem over here. So that's how you would go about doing something like this. I have done more about this if you want to see this in more detail with a similar problem, and actually a much more complex problem as well in terms of integrating uniform rods and a non-uniform rod. Then I'm going to put a link to that lesson in the upper right about now. So take a look at that if you want some more information. Let's talk about our third method for calculating the moment of inertia. This is really important. It's the parallel axis theorem. It's something that you're expected to know how to do. It didn't used to be on the equation sheet, but now it is on the equation sheet for AP Physics E Mechanics, so it is definitely expected that you know how to do something like this. Let's take a look at two examples. The first example is if you just have a hoop, which is one of the easiest objects. You can also, it's effectively the same value as like a point mass, you could say, in terms of the equation for the moment of inertia. So what are we doing here that's different? Well, what we're doing here that's different is we're going to find the moment of inertia for this object here, but we also have to figure out what's going on with this offset value. This offset value is the distance between the axis of rotation and the center of mass of the hoop. So if we find the moment of inertia for the center of mass for the hoop, and then we would need to add that to the offset value over here. So let's go about doing that. It turns out that they're basically going to have very similar equations here, at least to the outset, and then we do need to consider that this d, or offset value, is going to be considered 2 radii, so let's use that. So we're going to plug this value in, and we end up with this being our answer here. And that's a brief intro about how to use the parallel axis theorem for finding the moment of inertia or rotational inertia for an object that is offset from the axis of rotation. Let me show you one more example here though, just so you get the idea. In this case, we're dealing with a long, thin, uniform rod of length L and mass m about a perpendicular axis. So let's think about how to do this. So in this case, you've got the length of the rod. So we need to find the moment of inertia right here for the rod itself. And then the offset value, this offset value is really important. That's going to be the difference between the axis of rotation and the center of mass for the object that we're dealing with. So that's why we're going to say it's L over 2, because it's a uniform rod, which would mean the center of mass for the rod would be right in the middle. So 1/2 the length value, and so that's why we have L over 2, and then that is quantity squared. We do the math here, and to simplify, you end up with 1/3 ml squared. So that's how you go about doing these as a brief overview. If you want more information about this, I've got more information about this. I'll put a link up to the unit that we're dealing with right now. And I've done screencasts on an entire year of physics as well as most of the concepts for AP Physics CE Mechanics. So if you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.